Okay, so how would you guys make this graph? What type of graph would you make out of this? A bar graph. Why? Because it's the best for this scenario, right? All we have is what type of pizza people like. We could even make a pie graph if we want to. Get it? Pizza pie. All right. Okay. Right, and then we have the number of votes. So what's going to go on the x-axis then? The type of pizza, right? Because it's the most consistent, right? The most constant set of data. That means the number of votes is more variable. I don't think I need to draw the graph, do I? We can make a column graph pretty easy, bar graph. So let's go on to this one. This set of data. Now what would you put on the x-axis? What would you put? Would you put the plant group? Do we actually need the plant group in here? No, we don't need that information. It's just pointless information. So, cross it out. I would use pH of soil and average plant growth in centimeters. What would be on the x-axis then? Allie, what?
Soil.
Why? Yeah, they're smaller range, they're more constant, right? So let's make this one then. All right, so X, Y, then we have pH of soil. What I love about this, okay, is they probably took the same exact plant and planted it to figure out which pH is best, right? It's the same plant for every group that they did. But some plants would do better here than here, which is really cool, okay? Because I had a college professor that she thinks she found a new type of mustard plant that lived in acidic soil, and we went and tried to find it for our lab. That's what we did for one of our lab days. We missed class all day, and we're out roaming the hillside for this mustard plant. We didn't find anything, but it lived in a more acidic soil, which is kind of cool. Okay, so then we have 6.0, 6.2, 6.4, 6.6, 7, and 7.2. And that means we're going up to 53. Do I have to start at 0? If we're starting right here, 22.9 is the smallest. No, I'm going to start at 20, right? I don't need to start at 0. So 20, 25, 30, 35, 40, 55. All right, so 20, 30, 40, and 50. Okay, what type of graph should I make out of this information? It's the average plant growth. Right, if I had a question like we did on our graph, predict the rainfall from a year with 4 centimeter growth ring using this graph. Okay, predict the pH you would need to get a 50 centimeter of growth. What type of graph should I really use? Would I use a line graph? Is that what I would use? What do you think? Zach, what do you think? Ian's nodding his head. Yeah. Right, I'd use a line graph. What type of a line graph would I use? Would I just like connect the dots? No, I would do a best fit curve, right? You can do that. So, here we go. 6 is 25.4. 6.2 is 33. 6.4 is 50.8. And we have 53.3 twice. See if I can get it good. And then 7 is at 30.5. Let's clear down here. And 22.9. Is that good enough? right? I actually think if we did a 6.7, it would be a little bit higher, right? Because this is just an average bell curve, that's what it is. This is how your grades are too, usually. C, D, F, B, A. So whenever we get to like the end of the quarter, I'm like, look at your grades. And then I'll draw this graph really quick. And then I'll go, here's where yours is. And I'll go like this, because it's skewed to the left a little bit. And then I'll say, is my class too easy? Because your grades are showing that it is. That's what I'll say. You could say no, it's okay. No, it's good, it's good. Right, okay? So, right, because we're trying to find the average, that's why we do that. Right, the best fit model instead of, well, let's just connect the dots. Could you just connect the dots for that? Right, just with this information, yeah, you could just connect the dots, that's fine. But, if I'm gonna ask you a question about the averages, yeah, you definitely wanna do a best fit curve. So, let's look at a couple graphs. What's wrong with this one? Eliza, do you see it? Abby does. Abby, what you got?
Is it the data's wrong?
Well,
Shouldn't the more like consistent data be at the bottom?
yeah, so
X?
we got the trials, right? That's consistent.
Oh.
Right? Trial one. Is there any labeling down here?
Oh, no.
Do we
labels.
need any labeling down here though?
Yes.
Do we?
Yes.
Right? Maybe put types of drink, right? Because we got it right here. What type of drink it is, right? That we're watering the plants with, but we should probably put types of drink down here, right? Kason?
The numbers don't have anything showing how much they grow.
What are we actually measuring? I have no idea, right? Oh, well, it's 10, 20, 30, 40, 50. Oh, what does that mean, right? Was this 50 centimeters? Was it 50 millimeters? Was it 50 millimeters wide? I have no idea what they're measuring in, right? But we can glean some data from here that, right? Well, milk doesn't do a very good job in the first two trials, but in the third one, it does a decent job at growing plants. And root beer does decent in the first two and doesn't do a very good job in the third one, right? And then, of course, water does the best, right? It's a good experiment. You guys will actually do something like this for your pea plants that I give you. You can use root beer or milk, but you have to use water as a control. So, milk, root beer, don't do two, just do milk. Okay, because you'll be writing a hypothesis and everything today about pea plants, and you got to get it passed off. Okay, and you can only choose one thing that you're changing. All right, so here's just basic column graph. The one thing that I like about this graph is they could have had like 20 trials, and 17 of them could have been like this, and 2 of them could have been like this, and these are the only 3 that they put up there, so they could say that root beer grows plants, but it's better for you than milk. Right? Because scientists can skew whatever they want. They can say whatever they want in a graph because it's just a representation of the data that they want to represent. That's scary. That's really scary to me. So just be aware of that. All right, here's another, it's just an example of a best fit curve line graph. This is actually kind of how stars go. It's called the HR diagram of stars. And it goes on like luminosity and does all this other stuff. It's pretty cool. But that's just what it would look like, right? So this graph would really have a bunch of different dots from all the different experiments all around it, and we'd put a line through the dots. Okay. So, and here's a line graph that I really love because it has to do with the internet and the browsers that we use. And this is from 2009 to about 2016, looks like. Look where Internet Explorer was back in 2009. Look at how many % of people used it, right? This is good, it has percent and the year, right? So this is actually a really good graph, and then it has what everything is. So, Internet Explorer, that's Microsoft, right? And now they have Microsoft Edge as the new browser. It's supposed to be better. Because it is, because you can log into your Microsoft account and it saves all your stuff, passwords and everything, just like Google does. Notice Google Chrome shoots up. Right here, percent Firefox, notice it's pretty high. This is when I was in college. Guess what browser I used? What browser do you think I used based on this graph in college?
Firefox.
I used Firefox. That's what I used in college, okay? I thought Internet Explorer was too slow, so I used Firefox. Now, everything's on Google, even this slideshow is on Google, so I'm using Google now. Right, because I can save everything on there and I'm good to go. I love this one, Opera. I've never even heard of that internet browser before. Okay, I really like this one too, mobile versus desktop. How many people were using the internet mobile versus desktop, right? So notice here's desktop and mobile. Mobile's really small, and then it starts shooting up. Smartphones. Right in here is when smartphones came out. It's right in here. I had my first smartphone right in here. I was the only one in my family that had a smartphone. And unlimited data was $20 a month. Think about that. They could still do that. Easy. That'd be so easy to do. But it's all about making money. Fun. $20 a month, and my dad's like, I can't afford that. So I had to get off this plan and give up my smartphone. Okay? I want you guys to do this, but we'll do it later, right? When we're done filming the video. So we'll draw a best fit curve based on this data. So I'll have you guys do that. Ian, will you come up and get close so that they can do it? So you can just get something of the data so they can see the data. You guys on the video, fourth period, you're gonna make this graph on a piece of paper. Just make sure they can see the data. So pause it and, draw your graph because I'll be checking that when I get back. We good? All right, cool. Thank you, Ian. Okay. Let's move on to scientific method. So, scientific method, we've all done this before, right? But let's talk about it really quick. So it has 4 parts. I don't say steps because you can start wherever you want, right? I can start with an experiment, draw some conclusions, then find a problem with my experiment. And then write a hypothesis based on my problem, and then do another experiment. So, we usually start with defining problems. Like our problem the other day was, can I jump higher off of 1 leg or 2 legs? That was our problem, right? It's usually a question that you're asking. It's a question. So, define the problem. So, let's go to that. That's why I put this on here. Who, why, when, how, what, where? I don't know where that song was. It's like who, what, when, where, and why. I don't remember. I've heard that song. What? Spy Kids, yeah, something like that, yeah. I was like, I just remember. Right, that's defining a problem. Why is this happening? What's happening, right? When is this happening, right? So, how can I, right? All that stuff. So, a few vocab words we need to do. So, go to your vocab list. That is on page 14 and 15. 14 and 15. So, quantitative. It's a quantity. Was our information, our data we collected, quantitative or qualitative the other day with our jumping? Was there a quantity to it? Was there a number? Numerical value, right? So, quantitative is data that has a numerical value to it. It's numbers, right? So, this is quantitative, right? Then, qualitative is without numbers. So let me tell you about an experiment I did in college. I was really into, reptiles and stuff, and so I wondered if reptiles would get accustomed to a stimulus like a tap on their cage, just tap their cage, and they'd react, and then after a while, they just wouldn't react anymore. Because we do that, right? I wear a watch all day, I take it off, and my skin still feels like the watch is there, right? Because it's so used to having it there. Or I have a hat on, and then I'm like, where in the heck is my hat? I swear, somebody stole it. And everybody laughs until I notice that it's still on my head. But my skin and my hair is just so used to it being there, right? That I forget that it's there because it's on backwards or something. So that was my problem. I was like, do reptiles do that too? I just want to know. And so that was the thing. So I was just generalizing, right? I was just, in general, most organisms, mammals, have this, at least humans do. It's a generalization, right? Do we have generalize in our vocab?
Yes.
Generalize is, right? It's the most common type of thing we have, right? It's in general, humans should drink about a gallon of water a day. Right, that's a generalization. Or, in general, humans that have a smartphone or any device, electronics, are on them for 5 hours a day. That's crazy. That's actually true. Okay? And skeptical. We've talked about this. What's skeptical? I've said be skeptical already like 500 times. What does skeptical mean to you? What do you think, Mason?
Not sure.
You're not sure?
No.
You're not sure about something. Like, be not sure about it.
Yeah.
Yeah, so you're gonna question it instead of just believing everything you hear, right? You don't believe everything. That's being skeptical, right? Like, I was listening to the radio, and they came on the radio. It was John Tesh. If you know who John Tesh is, okay? And he's like, a new study says that dogs that wag their tail to the right are happier when they first start wagging their tails, right? And if it goes to the right first, then they're more happy than the dogs that wag their tails to the left. And my BS meter was like going ding, 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 ding. And I was like, oh my gosh, why does anybody even care about this? Oh my gosh, my dog wagged their tail to the left. Is she depressed? Is she so sad? Oh my goodness, right? So, what I did with it was I looked at my wife and said, honey, did you know that people that are left-handed are more sad than people that are right-handed? And she goes, are you serious? I'm like, yeah. And she said, why? And I said, well, because everything's made for right-handed people. I mean, look at these scissors. A lefty's gonna, struggle with these. So, right, your notebook is set up for a right-hander. Right, if you just want to go through the notebook. Lefties, I've seen lefties, they like going through on the left side first. Oh, right this way first. Everything's, even desks, like even desks here, right? If it's just a flat-out desk with a table and a chair, most of them are for right-handers. Lecture hall B, pull up the table, it's always on the right. And she's like, oh, that makes sense. And then I smiled, and she's like, oh, I hate you! So gullible. She's not as gullible anymore. I've taught her. Okay, so after we define a problem, we want to write a hypothesis. So here's what our hypothesis should be, right, based on our evidence. Right, most hypotheses are based on evidence and assumptions. Assumption in science is like an educated guess, right? But we use that assumption to write a testable statement, which is a hypothesis, right? Hypothesis is a testable statement. If you're not writing that down right now, you're not taking your notes right. Right? Hypothesis is a testable statement. Assumption is an educated guess. right? You have research now, so I'm like, okay, I think that I'll jump higher off of 2 legs than 1. Now, with that hypothesis, instead of saying I think, or if I jump off of 1 leg, I won't jump as high when I jump off of 2 legs. It's not if, it's when. So, I jump higher when jumping off of 1 leg than off of 2 legs. Is that a good hypothesis or is it a bad one? We did the research, is it good or bad? Should we change it to 2 legs than off of 1 leg? Yeah, we have the research now, right? We already did it. We know that 2 legs are jumping higher on average than 1 leg, so we should switch it, right? Switch the 2 legs for 1. But is this a testable statement? Can I test this? Yes. All your hypotheses should be testable statements. Right? I run faster after I lift weights than before I lift weights. Is that testable? Yeah, it is, right? Is it a statement? Yes, it's not a question. It's not an if-then statement, okay? If-then statements are 7th, 8th grade, middle school hypotheses. We want high school level hypotheses, okay? So I'll be checking for this when you write your hypothesis. So today, what I want you to do, I don't even know what that other word is. What I want you to do is think about the T-pline experiment, and I want you to write a hypothesis about it right here on page 9. It says, okay, try this, and write a hypothesis about what you want to test. Okay? That goes for you too. Okay? So I will be looking for your hypotheses right here on page 9. You can write it above the hypothesis section. I don't care if it's going to be a little bit longer. Make sure it's a testable statement. That's what I want. Okay? So